Hi everyone, today I'm going to use the textbook that we use in class because there's some really well explained stuff in there, and we're going to be looking at several things. We're going to be looking at power and efficiency, which I'll go through in a second, and then we're going to be having a look at paying for energy, okay, so like electricity bills and things. Okay, so the first thing I want to do, if I get to a question I'd like you to do, I'm going to ask you to pause the video and do that particular question. So we're going to start here. So in many parts of the world, energy for heating and cooking is obtained by burning fuel in an open fire. In this country, we use the gas or electricity for heating and cooking, and we also use electricity to run many other appliances. The first thing you need to do is answer this question. Write down 3 different electrical appliances that A, transfer energy by heating, and B, are used for things other than heating. So I'll give you an example. Transfer energy by heating. One of the most obvious examples is maybe a kettle, because it transfers energy as heat in order to heat up water for a cup of tea. Used for things other than heating, maybe something like a television, which is putting most of its energy, transferring most of its electrical energy into sound and light. Okay, so pause the video now and see if you can think of some more and write them down in your exercise book, please. Okay, different appliances transfer different amounts of energy. Now this is a good example that they've got here. For example, an electric shower needs to heat the water running through it very quickly. So it transfers a lot of energy in a short time. It can transfer up to 10,000 joules of energy each second. Okay, so because you want constant hot water, the energy has to go into that water and heat it up very, very quickly. So you have to put a lot of energy in a very short time. The amount of energy transferred per second is the power of an appliance. The units for power are watts. So we've got a new unit here, watts, and a capital W if we want to write it down after a number, or kilowatts. Okay, 1 watt is 1 joule transferred every second, and 1,000 watts is 1 kilowatt. Okay, so you can work, I'm going to just switch to my paper, you can work out what the power of appliances with this formula. So power, oops, my pen's not working, is how much energy is transferred divided by how much time it takes. Okay, so energy per time, energy per second, power. Okay, now just on that, because units, we're going to talk about how units are formed later. So we've said that power is energy which is measured in joules and time measured in seconds, and that would give us the unit W, or watts. Okay, so a watt is equivalent to joules per second. Okay, that's what that actually means. This joules divided by seconds, energy divided by time, is power. Okay, so if we wanted to write joules per second, we could replace that with a W if we wanted to. Okay, and as we were talking about the other day, if we have 1,000 watts, then we can call that 1 kilowatt. Okay, and we're going to be dealing with kilowatts a little bit later. So different formula there, energy per second. So it's not the same, it's how much energy per second is being transferred. So something which like an oven or the electric shower transfers a lot of energy per second compared to other appliances. Okay, so we can find out how much energy different appliances transfer by looking for their power rating. Okay, so there's a picture here of a hair straightener. Some of you might have these at home, and if you look very closely here, it says 40W. Okay, so what that means is that the hair straightener transfers 40 joules of energy every second. Okay, 40 watts is 40 joules of energy per second. Okay, the higher the power rating, the more energy the appliance transfers each second. Cookers, electric fires, and other heating appliances usually have higher power ratings than other appliances. Okay, another question here for you to have a go. What is the power rating of an electric shower transferring 10,000 joules per second? I'd like you to try and do it in watts and then in kilowatts. Remember, for every kilowatt there are 1,000 watts. And then number 3, an electric kettle has a power rating of 3 kilowatts. How much energy does it transfer each second? Okay, and that obviously, because it's how much energy needs to be in joules, and suggest why the kettle has a lower power rating than an electric shower. Okay, let's see whether we can do those. Pause the video. I will come back and I'll give you some answers to these later on. Okay, hopefully you've had a go at those questions. So we're going to have a look at this word here, efficiency. You might have heard the word efficiency before. Now, this is really useful to be able to work out, and it's getting a little bit more maths as well. It's essentially working out a percentage. So appliances do not transfer all of the energy supplied to them into useful forms of energy. Some of it is wasted, so we said dissipated before, didn't we? Some of it's wasted. The amount of useful energy transferred compared with the total amount supplied is the efficiency of an appliance. Okay? Wasted energy usually makes the surroundings warmer. So what they're saying is the wasted energy generally gets dissipated as heat if it's making the surroundings warmer. Now, you can use a special type of diagram. It's this arrow thing here, which is called a Sankey diagram, to show energy transfers. The width of each arrow represents the proportion of energy. So this width here represents the whole energy going in, and then you can see this is a small arrow with a shorter width is representing 4 joules, and this is representing 36 joules. So what we've got here is 40 joules supplied each second by electricity, because this is a 40 watt light bulb, so it's transferring 40 joules every second. Okay, now if we look at where that energy gets transferred to, we've got 4 joules becomes light, and 36 joules gets transferred as heating. Okay, now remember what a light bulb is supposed to do. It's supposed to give off light, so we're actually only getting 4 joules out of our 40 that we put in that are transferred as the thing that we want, okay, or the thing that we are supposed to be getting. The other 36, so a lot more of the energy, is being transferred by heat, which is not helpful. Okay, this is a dissipated energy. We're not using it really for anything useful, and all it's going to do is heat up the surroundings of the light bulb, give those air particles around the light bulb a bit more energy. So reminder then, here is the conservation of energy law. Energy cannot be created or destroyed, so the total amount of energy supplied must be equal to the total amount transferred or stored. So what they're saying is, because we can't make any and we can't lose any, if you put 40 into a system, you've got to get 40 out. So if you see 4 plus 36 is 40, you're getting the same amount of energy transferred as you put in the first place. Okay, so the way that we calculate how efficient this light bulb is by using this formula. It's really easy to do. You get your numbers from the Sankey diagram often. So efficiency is the useful energy transferred divided by the total energy supplied times by 100. So the useful energy transferred in this example is 4 there. That's the useful bit, the light. The total energy supplied was 40 there. And so we do that division. We do 4 divided by 40, and then we times by 100, because what we're doing is we're working out a percentage. We're working out the percentage that was useful compared to the percentage that was lost. So you can see, you probably worked this out, 4 out of 40 as a percentage, that's 10%. Okay, 10% of this 40 joules per second put in is transferred as useful light energy, which kind of consequently means that 90% of it is lost as heat. Okay, so not particularly efficient, and actually various suppliers of light bulb try and make their light bulbs more and more efficient, so that people buy them, because they're not then paying for electricity that's going to get wasted, okay, and energy that's going to get wasted. Okay, the efficiency of an appliance can never be more than 100%. Well, obviously, because if you put 40 in and you got all 40 of it out, that's 100% efficient. You cannot get more than that, as you can never get more useful energy out than the total energy put in. Okay, So a few more questions for you to have a go at, and then we're going to go over the page. Okay, right, so we've got a little fact down here. Many people in the developing world still cook on an open fire. A simple stove like this can increase the efficiency of the fire to over 50%. So if we've got a special stove, what we're saying is 50% of the more than 50% of the heat energy going in will get transferred into the food, okay, to heat it up or cook it. Right, here's some questions to have a go at. A modern efficient light bulb transferred 9 joules of energy by light every second. It uses 20 joules of energy to do this. Calculate its efficiency. So remember, we've got the efficiency formula here. Sketch and label, so just sketch, we don't need it to be completely perfect, a Sankey diagram to show the energy transfers. So you are going to draw something along those lines for these numbers. Okay, 9 joules of energy of light every second and 20 joules of energy to do this. So if it's using 9, you need to work out how much is getting lost as heat out of your 20 and try and draw a diagram like that to show that. Then all the energy used by a kettle ends up stored as thermal energy in the water, the kettle or the surroundings. Kettles are about 80% efficient. A kettle uses 20 kilojoules of energy to boil water. How much of this energy ends up stored in the water inside of the kettle? Sketch and label a Sankey diagram to show the energy transfers. And it is more efficient to boil in a kettle than a saucepan. Suggest why this is so. So think about the shapes of the two and how you would boil water in a saucepan, okay, and what that's going to entail. Right, by the way, I will put a PDF of these questions and this book onto the area, so you don't need to worry if you're struggling to get them done or you're struggling to read them on the screen. But I think the best thing to do is to have a go at them as you go along. And then I'll come back and I'll do an answers section later. Okay, right, okay, moving on to something else. So we're moving to paying for energy. Okay, now I'm sure you are aware that the energy that comes into your house via electricity is not free. You have to pay for it. So your parents and carers will probably receive an electricity bill, or possibly they might go to the shop and put money onto their electrical meter. There's various things that you can do in order to pay for electricity, but it certainly isn't free. Okay, let me just scoot that down so that you can actually read it. Okay, so how do we pay for energy? Most of the energy we use has to be paid for. Some of the energy we use is bought as fuel, such as petrol or diesel for the cars, or gas for cookers and boilers. When we burn a fuel, energy stored within the chemical is transferred by heating. Okay, so this is saying the gas in your hob, the petrol you put in your car, we burn it and then we release that chemical energy as heat in order to cook and things, or to heat the house in central heating, or if we're driving along, probably as kinetic. For electricity and gas, we pay for the amount of energy transferred. Energy companies call this unit, use a unit called the kilowatt hour. Now I'm just gonna, I'll read the rest of this and then I'm going to explain why this is a weird looking unit in a second. Okay, so to measure energy, a kilowatt hour is the amount of energy transferred in 1 hour by an appliance with power of 1 kilowatt. Okay, for example, using a 2 kilowatt electric fire, for 4 hours would use 8 kilowatt hours of energy. So energy use is power rating in kilowatts times by hours. Okay, so I'm going to go back to my paper just to have a look at units, because I said we were going to come back to units later. Now, with this one that's there already, we've got joules per second, but this new one is actually a little bit more, it's a bit different because we don't have the slash in there. So we've got energy use equals the power rating, so that's on the appliance, times by the time. Okay, so the energy use is in a unit, a really odd unit, the kilowatt hour with no slash in it. The power rating will be in kilowatts, and the time will be in hours, or H. Okay, so the reason that this doesn't have a slash in it, if you think about it, if you think about the algebra of it like you've done with Mr. Morkison, if we do a kilowatt times by an hour, we can write that as kilowatt hours like that. Okay, so whereas with the other one we're doing a divide, we're doing joules divided by seconds, so we would have to put a slash in there. If we did kilowatts per hour, then that means per hour this is how many kilowatts are being used. That's not the same as saying how many kilowatts have been used. So this is like kilowatts over an hour, and that's what that one is. This is like for every hour you use something with the kilowatts, you have to times them together because you're using the kilowatts times by an hour. Okay, so it's not correct. I don't think I explained that very well, did I? But it's not correct to do that because what you've put into it is kilowatt times by time. So you don't. This would signify kilowatts divided by hours. Okay, like this is joules divided by seconds. So you have to make sure that you don't get confused. Don't say kilowatts per hour, it's kilowatt hours, one whole unit, kilowatt hours. Okay, right, sorry if that was made that less clear than it was before, because I'm not quite sure I explained that brilliantly, but if you can just try and remember that because it's a times there, that's why you don't have the slash in your unit. If it was a divide, then you would have. Right, so what you would get in an electricity bill, you get what's called a meter reading. So on the electricity that's coming into your house, it will be recording how much electricity you're using in a certain amount of time. So it's usually something like monthly, it might be quarterly, which is a quarter of a year. So basically that just keeps getting higher and higher, the number. So this tells us the reading of the meter from last time, and then it tells us the reading this time. So since the last electricity bill, we have increased the number by 784. What that means is you've used 784 units of electricity. Okay, now a unit of electricity is charged at 15 pence. Okay, so to work out how much the cost of the electricity will be, you need to do the number of units times by the amount of money each one costs, because you've had 784 units and each one costed 15p, so you need to do 784 times by, now I would have done 0.15, so I'd have kept it in pounds, so I would have done, what was it, it was 784 times by 0.15, which is, if you imagine £1 as being that, this is 15 pence, because it makes the maths a little bit easier to do, and that would equal 117.6, which is effectively £117.60. Okay, now what they've done here as well is they've added something called VAT at 5%, which that you have to pay on these things. So they've worked out 5% of this and then they've added that on. Okay, so the way they've worked out 5% of this is, well, you can do it in two ways. You can either do 0.05 times by 117.6, okay, which will equal 5.88. So that's one way of working out 5% of this. Or I think you've just done this with Mr. Morkison, if I'm correct. Or if you want to, you can do, well, okay, we had £117.60, 117.6 in mathematically. If I wanted 100 even pieces of that, I'd need to divide it by 100. That will give me 1%, whatever that number is. I don't have a calculator with me to do that right now, but 1%, and then I want 5 of them, so I need to do 5 times whatever this answer was, because that will give me 5 times the answer, which will give me 5%, and presumably will give me 5.88. So there's 2 different ways. This and this are exactly the same. It just depends on which way you find it easier to work it out. Okay, quite often it's this one. So you divide by 100 to get 100 equal pieces. That gives you 1%. Then you times by however many percent you want. That's probably a bit easier to understand. This one involves an understanding of decimals and the fact that this is 5% equivalent times by this. It's up to you which one you want to use. Okay, so heating bills can be reduced by designing homes to make the most of the energy from the sun. This house is a triple glazed conservatory. So you've got lots of windows down here, which are triple glazed. That means they've got kind of 3 layers, thin layers with little tiny bits of nothing, vacuum in between, to really maximize the energy from the sun, so the energy gets trapped within the house. You could use solar panels and things, couldn't you, as well? A kilowatt hour is usually called a unit in electricity bill, so this is 784 kilowatt hours. Fact: nearly 60% of the price people pay for petrol is tax. People only pay 5% tax on gas and electricity used in their homes. That's this VAT thing. But factories and offices have to pay 20% tax on this, plus another charge called a climate change levy. This extra tax is to encourage businesses to improve their efficiency so that they use less fuel overall. And in fact, at school, we weren't doing very well on our electricity bill in the last quarter, so last quarter of a year, because we were doing things like having our heating up quite high and then having all those doors open. Remember when it was really cold in the corridor? And so we made some changes to keep those doors shut a bit more and trying to keep the energy in a little bit more, to try and reduce our bills. Clearly now we're going to have a very small electricity bill because we're not there, are we? Okay, so here's a question to have a go at. A 1 kilowatt electric fire operates for 5 hours. How much energy does it use in kilowatt hours? Okay, so 1 kilowatt, 5 hours. 1 kilowatt, 5 hours. Okay, that should be quite nice and straightforward. Suggest why energy companies do not use joules to measure energy. Okay, think about how many joules you'd have to write onto these bills and things. Okay, we can save money on electricity and gas bills by not using as much energy. Insulating houses and using more efficient appliances can help with this. Why will using a more efficient appliance help you to use less energy? So remember, efficiency is the percentage of energy that is useful. So in this case, not very much for this light bulb. This is 10% efficient. But why would using more efficient things mean that you save energy? Why do you use less energy if you've got more efficient appliances? Okay, so pause the video, have a go at those. Okay, so some things that I'm hoping you have seen before. This is a energy rating certificate that you would see on well, houses have them. When you sell a house, you will get an energy rating for the whole house, but you'll see them on appliances. So if you look you may have seen them on things like washing machines, dishwashers, big appliances like that. They'll have an energy rating, and it tells you some information. So this here is telling us that it uses 220 kilowatts per annum, which is per year. Okay, so that's got a high rating. It's an A+ rating, not the best, certainly not the worst, and you can see green for good down through to red for bad. Okay, so new appliances have energy labels to show how efficient they are. The more efficient the appliances are, usually more expensive than less efficient ones. So you're paying more money in the first place, is what they're saying, for a more efficient machine. Let's say it's a dishwasher, I don't know what it is, but you can work out something called a payback time, which we're going to come on to in a minute. Now, if you buy the cheaper appliances, then you're likely to be getting the less efficient ones. So actually, if you think about it, you're going to be paying for energy that gets lost as heat. So you need to think about which is best. I would probably argue that over time, getting the better energy one with the but more energy efficient one is worth the money. So you can work that out like this. So sometimes buying a new, more efficient appliance or improving the insulation can cost more money than it will save you. The payback time tells you how long it will take to save the money that an efficiency measure costs. Okay, so payback time is the cost of the change divided by the saving per year. So this is useful if you're trying to kind of budget in the future about getting things. So for example, for diagram D, which I'll have a look at in a second, it shows some ways in which the homeowner could save money. So we've got various different ideas here, and they're talking about the cavity wall insulation. Okay, so you're putting an insulator, which is a material that doesn't transfer heat very well, and so kind of traps the heat inside of the house. It costs £350, and the savings on your electricity bill will be about £100 per year. So if you look at what they've done up here, they said the payback time for the cavity wall insulation. So they've got £350, which was the cost of the cavity wall insulation, divided by the savings per year, which is £100. So that means that in 3.5 years you have paid back the cost of the insulation, and then after that 3.5 years you're going to start saving money, because you're going to be saving £100 a year and you've already paid off the £350 to put it in. Okay, so in long-term effect that is actually really helpful and useful, but in the short term it's fairly expensive, £350, isn't it? Okay, let's have a look at some other ones. Insulation on the hot water tank costs £60, saving £15 per year. So they put a little kind of jacket on the hot water tank. Draft proofing costs £50 and saves about £15 per year. So they've put little those little kind of fuzzy brush things on the bottom of the doors. Then we've got solar panel for hot water. It costs £3,500 per year. To put on. But saves £70 per year. So this is kind of links back to what I was saying the other day. It takes an awful long time to pay back the cost of putting solar panels on your house. So £70 per year saving on the electricity bill. Loft insulation costs £150, saving around £150 per year. And then double glazing, which costs £3,500 and saves around £200 per year. Okay, so there's all sorts of different things here, and it makes that one look a bit cheaper now, doesn't it, when you see these costs over here. Right, so you're going to have a go at working out some of the payback times for these. So why should you work out the payback times before choosing a new appliance? Okay, number 4, use the data in diagram D to calculate the payback time for A, loft insulation, and B, draft proofing. So remember to do this, you're going to need to look for the costs, so loft insulation and draft proofing. You need the cost of the change divided by the saving per year, and that will give you your payback time in years. Okay, so you've got 2 to do, loft insulation and draft proofing. Suggests why the information in diagram D does not give exact values for the savings for each modification. Okay, so these are approximations, savings of £15 per year. Why would that not be exact? Think about things changing. You might know, I'll give you a bit of a clue with this one because you might not know much about this, but there's lots of different suppliers. They cost different amounts of money to they're all competing against one another, so often people change from like British Gas to Npower or whatever, and they save a bit of money. So it's not an exact science. There's also, if you think about it, that these are approximations, because actually for a specific house they're just estimates. We don't know how much draft there was before and how much this is really going to change. Same with this, like the thickness of insulation, is that going to change, etc, etc. There's loads of different factors involved in that one, so maybe just try and do a little summary of what I just said. Number 6, Mrs. Holman is choosing a fridge. Fridge A costs £120 and costs £27 per year to run. Fridge B costs £150 and costs £22 per year to run. Which one should she buy, and explain your answer? Okay, so in doing this you might want to talk about efficiency ratings, you might want to talk about the payback time, etc. Okay, right, I'm going to leave that there so that you have some time to actually do the questions and think about them. I suggest that you write down a few things, a few notes from this video as well. Okay, so you've got a little bit of a summary of what we've talked about, so there's quite a lot in there, although it's not hopefully too tricky, this stuff, and then some questions underneath. All right, have fun, bye.